Okay, thank you for inviting me to be here, and thank you for providing the weather. So this is a slight change in topic. I'm going to talk about something that some people call low-energy particle physics that has a lot of impact in high-energy particle physics, but perhaps not so many equations. And so these days, when we talk about dark matter searches, the motivation is not really something that we need to stress over several slides, and so I'm just going to put it here in the corner, that 96% of the energy density of the universe we do not know what it is, and so we spend a lot of time studying the other 4%, but we need to understand what this dark matter and dark energy really are. And so in terms of motivation, I think it's sufficient to remind you in this way. There are many candidates that could explain the dark matter in the universe. I'm going to just list a few, but I'm going to choose one, the weakly interacting massive particle. That is the one that attracts most experimental effort at the moment. And I'm going to tell you very briefly how do we go about trying to find these weakly interacting massive particles with underground experiments. There is great complementarity between direct dark matter searches and accelerator searches for dark matter and physics beyond the standard model, and also with indirect searches for dark matter annihilation, for example. And I'll have a couple of slides on that. I'm going to describe some of the technologies, not all, because this is a very vibrant and diverse field, but I'll describe a couple of the technologies that are at the forefront of these searches, and then list the experiments that are presently leading in sensitivity and the ones that I expect, at least in the next decade or so, will be able to tell us something new about dark matter. As I mentioned, there are many candidates, and the list is probably larger than this one. And some go out of fashion and come back into fashion. So, for example, I have sterile neutrinos here, and then I remove them, then I put them back again, and so on. So they are also a reasonably good candidate. But two of the oldest are weakly interacting massive particles and axions that are still really at the top of our priority list, at least in terms of experimental searches. They both solve the dark matter problem very nicely. They solve other problems as well, and in particular, WIMPs could have something to do with the stabilization of the electroweak scale and the hierarchy problem, whereas axions were actually brought in to solve the strong CP violation problem. And so these things are very attractive because they also solve something else in physics, and in some cases they were brought in to address other problems, not exactly the dark matter problem. So I'm going to focus on WIMPs, which are stable or at least very long-lived particles. They are neutral, non-relativistic in the early universe. They are heavy, ranging from as heavy as an hydrogen, as a proton, up to several tens of atoms, for example, of heavy atoms. And we know they interact via gravity, and hopefully they interact via the weak force as well, and that would give us a mechanism to produce them and to detect them in the laboratory. And WIMPs are really nice dark matter candidates. They are sort of ideal lambda CDM dark matter candidates in the sense that they solve all the problems related to dark matter, or at least almost all the problems, in terms of the astrophysics, in terms of the cosmology, and in terms of the particle physics. There are things we should keep in mind. They do not solve all the problems. For example, one might ask, why is the abundance, the relic abundance of WIMPs, which are a thermal relic from the early universe, why is that comparable to the abundance of baryons today, which have a completely different production mechanism and have to do with the matter-antimatter asymmetry, for example? So one might ask, why are these two quantities of the same order of magnitude, at least? So the three ways that we look for dark matter presently are direct detection, which is what I'm going to focus on. And here we are trying to measure a scattering cross-section between a slow-moving heavy particle, such as a WIMP, that comes into a detector material, scatters off the nucleus of an atom, and this nucleus recoils, not very fast. So in condensed matter, we are talking a few tens of nanometers, a few hundred nanometers at most, and deposits some energy in the medium in that way. Unfortunately, we understand that not many creatures can cause nuclear recoils in matter. So we are talking about WIMPs, but also neutrons and some low-energy interactions of neutrinos, and that's probably it. Whereas most radioactivity around us and most backgrounds for these searches cause electronic recoils. For example, gamma rays and charged particles interact with atomic electrons, and they create electronic recoils. And if we have a way of separating nuclear recoils from atomic recoils, we can go a long way to reject backgrounds in these searches. The observables that we can rely on are the dependence on target mass, on A, the dependence on the target spin, We could look for annual modulation of these signatures of the scattering rate, directionality in gases detectors, for example. And these are the things that we can pull out from some of these experiments, not all of them from the same targets, but these are some things that we might be able to do. This probes the dark matter at the position of the sun, or the position of the Earth in particular. So this is our dark matter. And we can measure the mass of that particle if the particle is not significantly heavier than the mass of the target. There are also indirect detection techniques. So we are looking at cosmic rays from dense regions in the universe, or even from the denser regions of our galaxy. And we could look for gamma rays and neutrinos, and we are probing either decay of dark matter particles or an annihilation cross-section. These are very challenging searches. I'll show you one example later. The backgrounds, especially from the galactic center, are not really very well understood, and the annihilation rate goes with the square of the density, which makes matters a little bit worse. And also, of course, there are accelerator searches where we look for a production cross-section via missing transverse energy, mono-X, mono-jet, mono-photon, mono-Higgs, and so on, searches, dark photons, and etc. The mass measurement may be poor, at least initially, because in this case, for example, missing energy, we are looking at the sums and differences of masses of particles that are produced in pairs. And can we really establish that the particles we find are the dark matter, or they can be just one component of dark matter, but not necessarily all of it? So I'm going to highlight the complementarity over a couple of slides. So this is the first one. So I'm going to refer to the spectrum of theory space here, where we can go from the very simplified effective theories on this side all the way over to the UV complete theories on that side, and minimal supersymmetries here, and supergravity, universal electron dimensions, and so on. Just to highlight how complementary searches at the LHC and direct searches are, for example. So this allows us, this is a scan, a global fits study of a scan of the minimal supersymmetry 15 parameter model, and we can plot the spin-independent scattering cross-section against the mass of the particle, in this case a neutrino. So this is exactly the parameter space we plot in direct searches, and you can see a couple of things from this plot. You can see that the mass, the range of mass is favored by these experiments, and we are talking here between about 50 GeV and just above 1 TeV are really the ones that are accessible to direct search experiments. The cross-sections, a bit less so. So in this case, direct search experiments cut about here at 10 to the minus 10 or 10 to the minus 9 picobarn, and can come down to about here, whereas this particular model predicts sort of a viable fits leaking down to much lower cross sections. But the second thing you can see is that coming from the top with experiments like Xenon 100 and Lux, direct search experiments are really sort of constraining a lot of these minimal supersymmetry models, and not even to mention things that stayed up here, for example, constrained minimal supersymmetry and other simpler models. This excludes the null SUSY searches at Atlas. If I add the results for this particular model, the effect is actually quite small. So the cyan color here means that there's an impact of less than 1 sigma on the delta chi-square for that particular model. But here, sort of, I was a little bit provocative in choosing a particular fit which excludes G minus 2. If you do not exclude constraints from Z minus 2, the upper plot does not change very much, but in the lower plot, the LHC does a much better job at excluding actually quite a lot of this parameter space. So there's quite a lot of complementarity if you look at it from the perspective of the scanning of very complex models, in this case, a 15-dimensional MSSM. You can go all the way to this side of the simpler effective field theories, and something that has been a concern in direct dark matter searches has been that these theories actually may not treat properly the fact that the mediator mass is assumed may not necessarily be very large. And so to try to mitigate that, as a new class of simplified models that have explicitly in them the mediator mass, and then you can plot. So in this particular model that I'm plotting here, there's the mass of the dark matter particle and the mass of the mediator. There's two other parameters which are couplings, which are made equal in this case, and you can see this is the result from Lux and the result from the LHC, and you can see that at least for this particular channel, which is a vector interaction, these things are very complementary. Looking up into the sky, so then we have complementarity between direct searches and indirect searches. And this is a plot from the the Fermi gamma ray satellite that seems to suggest an excess of gamma rays coming from a few degrees or 20 or 30 degrees from the galactic center. And if you interpret this excess in gamma rays as a dark matter particle annihilating at the center of the galaxy, then the authors ascribe this to a 30 GeV particle with an annihilation cross-section of 10 to the minus 26 centimeter cube per second, which is actually quite a good velocity average cross-section for a thermal relic, which is what we believe WIMPs to be. The problem is when you translate this into a spin-independent scattering cross-section, which is on this axis and this is time, you'll see that this translates to many, many models. And so the same observation may be accessible to experiments such as LUX or future experiments such as Xenon 110 and LZ, or it may not be accessible at all if it's buried inside the background of astrophysical neutrinos. And so in order to pin down the properties of the particle and the mass of the particle and the spin of the particle, we need to address the dark matter problem from all these avenues. And so looking for the scattering of particles from terrestrial targets, so this is how we estimate the WIMP nucleus cross-section. So we have to bear in mind that in our experiments, the particles do not scatter off protons or neutrons, they scatter from a nucleus, and that's what we measure. We need to know two things. We need to know how many dark matter particles there are, and we need to know how fast they are moving. And so we assume very simplistic models of the astrophysics, in particular that the dark matter halo is three-dimensional. It's very extense, stationary. It has no lumps. It's a uniform profile with a density about r to the minus 2, at least where we are at the position of the Earth, and a local density which is determined dynamically to be about 0.3 GeV per cubic centimeters, which actually there isn't a huge error on this quantity. Maybe we're talking about 50%, certainly not much more than that. So that means that there's about one WIMP per pint in space on Earth. The velocity distribution is essentially a Maxwellian distribution which is truncated at some escape velocity. So this is the width of the Maxwellian distribution. This is the escape velocity. That means that WIMPs that are present in the halo above this velocity will have, if they were, they would have boiled off from the galaxy and evaporated. And on top of this, we've got the Earth velocity around the Sun and the Sun's velocity around the galactic center, which changes the average velocity of this distribution. And using these two things, we can calculate a scattering rate, which is the number of scatters per unit recoil energy that we essentially express in events per kilogram of target mass per day per keV, which depends on the cross-section that we are trying to find, on the density, a few masses, a nuclear form factor, and an integral over the velocity distribution for these WIMPs. Essentially, if you simplify this, you end up with an exponential, which is represented here, so the scattering cross-section, and this is the recoil energy, and you can see that this is a very small energy, which is really the challenge of these searches. A lighter WIMP would produce a steeper spectrum than a heavier WIMP, but our observation would be a number of events, hopefully with a reconstructed energy above some energy threshold from this detector, and then try to understand which exponential this is most consistent with. So of course we would like to compare our searches with accelerator searches and indirect searches by calculating a scattering cross-section on protons and neutrons. And to do that, we actually don't know if that interaction is spin-independent or spin-dependent. And if it's spin-independent, we benefit from, so that's the cross-section on the nucleus, and this is the cross-section on the proton or the neutron that we consider to be equal in this case. And in the spin-independent case, we benefit from a factor of a squared, so that's the atomic mass squared, which really gives quite a lot added sensitivity. This is because the scattering is coherent across the nucleus. It's a low-energy process. In the case of the spin-dependent cross-section, the axial vector interaction, that factor of a squared is replaced by a more complicated factor that has couplings to protons and to neutrons, as well as spin structures for protons and neutrons in the nucleus, but this number essentially is small, and that number a squared is quite large. So we are not quite so sensitive in the spin-dependent channel. In terms of complementarity, therefore, we have targets which are more sensitive to the WIMP-neutron interaction, others that are more sensitive to the WIMP-proton interaction, and that has to do with this spin, the average of the spin structure over the entire nucleus, and we have targets like xenon and germanium that have good values for neutrons. We've got other, for WIMP-neutron interactions, we have fluorine and iodine that have high values for protons, and the same targets are not necessarily the best in each channel. There's also some target complementarity between to do with the mass of the WIMP we are trying to detect. For example, if you're trying to detect light WIMPs, kinematics is a fact of life, and you would rather have a light target, something like silicon, to create a larger nuclear recoil, larger energy nuclear recoil. If you have a heavy WIMP, another factor that comes into play is the form factor, which for some materials, for example, for xenon, is not very favorable, and so a heavy WIMP looks a little bit like a very heavy WIMP because the form factor just kills over. And so to have a complementarity of targets is also beneficial in several cases. So the experimental challenge is difficult because the rates that we are trying to detect, and this is a WIMP which is not around the corner, but it's maybe a factor of 10 or 20 where we are today, the rates here are a few events per ton of material per year, and the threshold energies that we are talking about should really be here in the few keV. And both of these things together is what makes it very hard. It's very easy to look for low energy events, be it nuclear recoils or electron recoils, and it's also not hard. We know how to look for rare events as long as they are at high energy, but it's to do both at the same time that's really very hard. And another complication is that there is no trigger, so we are always 100% of the time live to the signal, but you're also 100% of the time live to the background. There are several technologies that can address this, in particular to reach the levels of discrimination between electron and nuclear recoils that we need to reach. Some of them are based on ionization detectors or scintillation detectors or phonon bolometric detectors, or a combination of two of these. And in this case, it's actually more common these days to have combinations of ionization and scintillation detectors, for example, the two-phase xenon TPCs, or to have combinations of ionization and phonons, for example, the cryogenic detectors, germanium detectors. And so there's clearly, it's a very active field. As you can see, this is not an exhaustive list. Some of these technologies can address higher mass WIMPs, and others can address lower mass WIMPs. So this is the status. This is where we are at the moment. So this is the scattering cross-section for the spin-independent interaction, which is unknown. This is the mass of the WIMP, which is unknown. And the shaded lines here are results, experimental results. This is the results from LUX from 2013, which leads from higher mass down to about HeV or so. And then here we've got the cryogenic detectors, super CDMS and Cdms Light coming in. We've got here a rather curious CCD-based detector that I'll talk about in a second. And here, this is the limiting background from astrophysical neutrinos. So this is when the systematic uncertainty on this coherent neutrino scattering of these neutrinos of atoms in the target become a limiting factor because you can no longer subtract that systematic uncertainty. And so just to, although I like this plot quite a lot, just to not to sort of give you any illusion that we have not been working hard, this is a very large number of orders of magnitude. And in fact, we started here in just before, in the late 1980s, and we are here now. And this is 3 decades of effort, nearly 3 decades of effort. And we've gone down 5 orders of magnitude in improvement in sensitivity due to reduction in backgrounds, larger target sizes, and better thresholds. So this is actually sort of quite a remarkable progress for any physics, for any field in physics. And clearly, in the last few years, it is becoming clear how we move forward, at least what are the leading technologies that allow us to move forward. If we want to go down, we need size, and we need exposure, and we need background. We need lower background. If we want to go to the left, we really need to work on the energy threshold, and we also need lighter targets. And I think this is more or less the consensus. I wouldn't say consensus maybe, but most people will agree that it is a fact that the noble liquid detectors are pushing down very quickly in this direction, whereas the cryogenic detectors, the cryogenic semiconductors such as silicon and germanium are pushing in this direction. And so let me just bring the lawyer out just to say that I'm going to summarize just the ones that are world leading at this very moment in time, as well as the ones that I think will have an impact and have something to say about dark matter in the next decade. What comes after the next decade, we don't know. There are, of course, other technologies that could come and leapfrog these, But clearly, I think we have a good understanding now about where we're going to be in about 10 years from now, not even that. So just a disclaimer here, which I almost missed. I work on Lux and LZ, and fortunately these feature in the next few slides. So the first one I want to sort of talk about is the dynamic experiment, which leads at very low masses. This is based on CCD technology, which is really rather unusual. I remember the first time I heard about this, thinking they cannot possibly have any reasonable target mass. And in fact, they don't. They have 1 gram per detector, but the fact is they could still have a world-leading result with a very light detector. This is a special kind of CCD that you can see here on the right. And the idea is that you have very, very low noise. You have no particle discrimination, but you have sort of good track resolution. And you can determine what is a muon, what's an alpha particle, what's an electron recoil. And then things that are very small, diffusion-limited clusters of pixels could be WIMPs. They could be also X-rays. They could be neutron interactions. So they have a very low threshold, about 50 electron volts, which translates to about half a keV in nuclear recoil energy, because nuclear interactions are quenched in scintillation and ionization. And so their sensitivity is world leading at very low masses, as I showed earlier. Then the cryogenic detectors, in this case, we are trying to measure phonons. This is a phonon signal. In some cases, it's a thermal phonon signal. In some cases, it's an athermal phonon signal. If you really want to scale the size of these targets, it should collect an athermal phonon signal. Otherwise, your temperature increase when you deposit energy in these detectors is going to be inversely proportional to the heat capacity, so ideally you'd collect the phonons before they thermalize. You can and should combine the phonon readout with ionization or the phonon readout with scintillation. So this is what CDMS and Edelweiss do, and there's CDMS crystals here, germanium crystals, and Edelweiss crystals there. Or you can combine them with scintillation, and that's what the CREST experiment does. So in this case, we've got scintillation crystals operated at very low temperatures. We are talking a few millikelvin, and combined with the phonon readout. Super CDMS and CDMS Light are the sort of the set of experiments that lead at very low masses above DAMIC, but before the noble liquids. They are located at the Sudan mine and in the infrastructure that was used previously for CDMS2. In the case of super CDMS, this is essentially the phonon ionization structure that I mentioned before. You've got crystals that have phonon detectors interspersed with ionization detectors. And in this particular run that was reported this year, they use about 7 of the 15 detectors installed that have very good, very low thresholds, and they do a special analysis at very low energies, up to 10 keV, with some discrimination, so sacrificing discrimination in favor of threshold, and they achieved a very good result in that way. CDMS Light is quite a sort of a new development. It's quite an interesting development, where you forego the phonon channel, but you apply a reasonably high electric field to the crystal, and when the charge drifts and you reach a saturation velocity, you start emitting phonons, and these are sort of these Luke-Nagano phonons, and then you use the phonon readout to read this new phonon signal. Of course, you have to forget about the original phonon signal because you've lost, that one is buried under the Luke-Nagano signal, but you can have really quite impressive thresholds, and their result comes from a 0.8 keV threshold. So next on to the two-phase TPCs, which lead at higher masses. In this case, we've got a detector, a chamber made from a highly reflective material, usually typically Teflon, and these detectors in the case of Lux and Xenon 100 are between 100 and 200 or 300 kilograms of material at about minus 100 degrees centigrade. The particle comes through and it generates a flash of scintillation light, which we detect with photomultipliers top and bottom. You move the charge that is deposited up to the surface of the liquid and you emit it into the gas. The ratio of these two signatures tells you what kind of particle it is, if it's an electron recoil or a nuclear recoil, and it also allows you to localize the event with very high precision in 3 dimensions, which is very important if you want to get away from the walls, because that's where your backgrounds are coming from. And Lux had excuse me. So Lux has 250 kilos of active mass, and one of the innovative things that Lux has done is actually to be able to calibrate the signal in situ with dispersed sources. So there's two very clever sources, krypton-83 metastable and tritiated methane, which are dispersed throughout the target, and then they can be removed or decay inside the target to be able to characterize the whole detector down to really very low energies. A second test that we are doing is with the neutrons, a DD generator embedded, which is outside the shielding water tank, delivered through a pipe, and the detector is large enough that we can now reconstruct two scattering vertices inside the detector and do kinematics with that to measure the response to nuclear recoils to very low energies. So this is the result from LUX. This is the higher ratio of ionization to scintillation as a function of more or less recoil energy. You can see some background here, which is consistent with that calibrated via the tritium source, and you can see the signal acceptance here, which is essentially reasonably clean, and this is totally consistent with the p-value of 0.35 with the background-only hypothesis. So we also have single-phase liquid argon, which is now switching on at SNO lab. So in this case, it's not a two-phase xenon TPC, it's a single-phase liquid argon looking only for scintillation with 4 pi coverage in photodetectors, and that is essentially doing pulse shape discrimination in a 3.6 ton liquid argon target. And then the xenon 1 ton experiment, which is now under construction at Gran Sasso, is going to be, after DEEP, is going to be the next system that probably will be at the forefront of these fields. The water tank is pretty much constructed, and the cryostat is I think, either being welded or almost finished too. And the sensitivity predicted by xenon 100 is 210 to the minus 47. And after that, we'll have LZ, the LZ experiment at the Sanford lab, which is a 7-ton TPC, again of the same types as LUX and xenon 1 ton, surrounded by other detectors. There's a liquid scintillator Vito and a xenon skin detector here to go about a factor of 10 below xenon 1 ton. So this is where the field is going to be about 2021 or thereabouts. So LZ will be down here, xenon 1 ton, and there's LUX, and DEEP is here somewhere. And in the low mass regime, we have super CDMS at SNO lab. And so those are my conclusions. So we have the tools now to explore most of the favored region of parameter space down to the neutrino floor. And so I think the field is as vibrant as it's ever been, and there are really literally dozens of experiments out there. But I think we now have a better understanding in the last few years of what are the technologies that are going to do heavier WIMPs, that are going to do lighter WIMPs, and I think we can move more quickly now. And there is also great complementarity between direct, indirect, and accelerator searches, and the motivation is very clearly there, so we need to keep digging. Thank you.
Okay, we have time for a couple of questions. There in the middle.
So what are the attempts done right now to try to understand the discrepancies like between Dama Libra and other? The fact that there are some, for example, there was a paper yesterday or this morning showing that Dama Libra could be oscillation from neutrinos combined with cosmic muons, both producing neutrons.
I don't know the answer to that. I mean, the problem with the Dama result here is that it now sits so high above the present exclusion limits that, I mean, LUX would be seeing thousands and thousands of events if this were dark matter, at least in the way that we understand. The problem with many interpretations of Dama, either be it in nuclear recoils or in electron recoils, is that if you look at the result from LUX here, where you can really see that there is no significant number of nuclear recoils. There is actually also no significant number of electron recoils. This detector is almost of the same size as Dama, 250 kilos of target, which is what Dama have. And in this case, we do not even see enough electron recoils to modulate anything, let alone nuclear recoils. And so the answer is, I don't know. I think we have kind of run out of explanations for Dama because we see no interactions in this medium, either electron recoil or nuclear recoil.
Okay, there was one in the middle. Raise hand, please. No? Okay, let's go here.
I could like to pick up on the last statement you have in your conclusions about how complementary are all the searches. So, I mean, in the big picture, you said that in order to go to lower values of the wind mass, you need to go to a new generation of detectors. At the same time, that's precisely the region where the LHC can say something, going a little bit away from all the troubles for applying effective theory. So very light winds might be a region where safely we can say something altogether. So my question is, how you see this? I mean, do you plan to, we sit together and we try to do something consistent?
Absolutely. This region, and that was one of the reasons why I put the dynamic result there. This is kind of new for us. I don't think, at least I did not see the field going in that direction a few years ago. And partly because of the success of the TPCs creating sort of a gap here, and partly because there are genuinely well-motivated theories there, I think we have not really experimentally explored this region probably as much as we have explored this region. So I think a few years ago we thought we were going to run out about here, and we were really not focusing on the low masses. Now there's an understanding that actually with detectors that need not be very large, we can actually address that region at least to the GeV scale. What comes below the GeV scale, it's going to be very hard, I think, but you are right that there is some complementarity, and that accelerator search is at some point.
Yeah, I mean, my point is that below 1 dB for the LHC is almost free to go, pretty much. The only limitation is when you put in these terms, how do you apply the effective theory, and how sure you are about the fact that you're applying in the right place. So, but I think very, very light winds, I think we are safe. So we could put here, I mean, in the very, very light wind scenario, so at the level of 1, 2, 3 GeV, even if the LHC results are using the effective theory that is very questionable at very high wind masses, at those masses, I think we are not completely wrong, let's say. So,
right.
So it would be nice to have in this plot these kind of things.
So that's why I included this plot on these new types of simplified models that try to address this via including specifically the mediator mass. And here, in this case, you can really see the complementarity.
Okay. Can you go back to this next to last slide, which you just said? The future? No, to the end. Yeah. So, yeah, this one. So there's one thing which I'd like to comment, namely Xenon 1-ton, which is being constructed and is going to start detect next year, has built in an option that's not known much, namely Xenon N-ton. Everything is laid out for N-tons. It's just once the detector works, there will be a new TPC which goes in quickly so that the jump to N-tons can happen in a very short time.
Had I not run out of time, I would have mentioned that it was here and there.
Yeah, and that's, as I said, everything is built for N-tons already. It's just the TPC that has to be affected.
Yes, I understand that. But so I kept two systems that sort of have really well-defined engineering. I think Xenon N-ton is an intermediate case where some of the engineering is there, not all of the engineering. But I had intended to mention this had I had more time.
I just comment because it's missing on your sensitivity line. It's probably the first step moves in the generation 3 case.
That's right. But I take the view that, I mean, it's very easy to draw sensitivity lines on a plot. And many have come and gone over the years. I think it's a different matter to have a system which is engineered, which has a clear strategy to achieve that sensitivity. And Xenon N-ton may well be in the next year or 2 years that it is one of these systems.
Okay, I think we need to cut it here. Let's thank the speaker one more time.